Hello and welcome to another video. In this video, we're going to be working on minimum difficulty of a job schedule. And in the problem, you're given a schedule list of jobs. In D-Days, jobs are dependent. To work on the ith job, you have to work on all the jobs before it. So you have to do all the jobs in order. You have to finish at least one job every day. And the difficulty of a job schedule is the sum of the difficulties of every day. And the difficulty of a day is the maximum difficulty of a job done that day. So you're given an integer array job difficulty and an integer D. And the difficulty of the ith job is job difficulty I. Return the minimum difficulty of a job schedule. If you cannot find a schedule, return -1. So let's look at the examples. So in this first example, they are saying that this is what you want to do on day 1, and this is what you'd want to do on day 2. So this would be 6 on day 1 and 1 on day 2, and we'd get 7. In the second example, you have 3 tasks but 4 days, and you have to do a task a day, so this is not possible, so you should return -1 here. And in the third example, you have 3 days, 1 task a day, so that you just do 1 a day. So this is pretty easy to recognize that, I mean, this might not necessarily be the best solution, but at least it's pretty easy to recognize that this should be in a DP category, right? Because you're essentially asked to divide up jobs into days, right? And tasks depend on each other. So the way you divide, like if you do some jobs in one day, then the jobs you do the next day and so on all depend on each other, right? You have dependent states, and you have pretty small constraints, right? Like this thing doesn't really matter because you're almost never going to use this. But the thing that will matter is like obviously the index and something else. So you have pretty small constraints and you're asked to divide your jobs. So immediately, I'd say almost for most of these problems, immediately you want to look for DP. And then if you can find something DP, then there might be something better, like a stack or like a greedy or something. But I think for most of these problems, the main thing you want to look for is it like a sliding window 2-pointer type thing, or is it DP? And that's going to be like almost like at least half the problems. So you obviously can't do like a sliding window because you have to divide this up into like a bunch of chunks, and it's kind of hard to say like how do I measure like what the chunks are. Like if I say this chunk, then I have a bunch of other chunks and other chunks. So when you have to divide your stuff up into like 10, 20 chunks, then DP is probably going to be better. So let's figure out how we can do this in DP. And so as always for DP, we need a couple things, right? So we need states, we need base case, and recursive case. And essentially you're being asked, like you have some jobs, and you're being asked, so let's actually draw out these jobs. Let's say we have like these jobs. Let's just say we have these. We have some array. We'll have some numbers and so on. So let's say we have like 7, 8, 5, 2, 1, 3, 6, 12, 15, 14. And let's say we have like 4 days. So essentially, like what would we need? What's the minimum number of states to know how to actually divide this up? Well, obviously, you're going to have an index in almost every single DP problem, so that's going to be 1. So index. But what else do we need? Like when we divide these things, like what information do we need? Well, it kind of depends how we do this problem. Like if we choose like a take or don't take scenario, that's going to be kind of hard, right? Because for each day, we have to get the maximum of all the jobs taken for that day. So we can't really do like a take or don't take, but what we can do is we can have like some start index, and instead of take or don't take, we can just say like, okay, let's try to recurse everywhere from that start index forward, right? Now, obviously, you might be able to do some optimizations, but this should easily be fine. So essentially, we'd say like, okay, let's start here. Maybe we'll take this job on day 1. Maybe we'll take these 2. Maybe we'll take these 3. Maybe we'll take these 4. Maybe we'll take these 5, and so on. Just keep doing that all the way down. And all we need to really keep track of in that case is just, like let's say we take these 5. We just need to keep track of like what's the maximum element in here. And then what do we need to pass down into the next state? Well, we need to pass down, obviously, the index. But we also need to pass down how many days we have left or how many days we've like used, right? So like days left or days something, right? Days left. And so because we need to know, like, once we split this up, like, did we actually, like, let's say we split it up into this chunk for day 1, this chunk for day 2, this chunk for day 3, this chunk for day 4. Now we're over here. We actually need to know, like, hey, we actually don't have any more days left. And there's kind of no way around that. So you need that state, and that's pretty much it. So an index and days left will tell you everything you need. And so now let's think of how you would do this. And the way I personally decided to do was instead of days left, I just started at day equals 0, and then I loop, or I just increment by 1 every time I recurse, right? So I start at like I start over here, I'm like, oh, I'm on day 0, then I choose to take some number of days, let's say this, then I recurse here, then I'm on day 1, choose to take some number of days, day 2, and so on. And then based on that, let's figure out a base case. So one base case, the obvious base case that you pretty much always have is out of bounds, right? So our index is the length of our actual thing. What do we want to do? Well, there's a couple things, right? And so you have to choose to take one task every day, but what if you didn't, right? Like what if in our recursion we're like, you know what, we'll just take the whole array day 1, right? Like we just said, okay, let's take this whole array day 1. Now we're over here with 3 days left. What do we do there? So there we'd want to make sure that never gets used, right? And because we're trying to minimize that, so we are going to have 2 cases. So A, we have days left. That means we didn't have a task every day, so we just want to return infinity. Otherwise, we don't have days left. So if we don't have any tasks left and we don't have days left, we just want to return 0, right? Or if we're adding all this up. And there is one other case where we just have, depending on how you write this, once again, you can have a check to avoid this. I personally didn't. I just said, like, let's just split it up however I want, and then we'll figure it out later. So if that's the case, then you're also going to have this other case of no days left and not out of bounds. Then we'd obviously want to return infinity as well. For example, let's say we take this day 1, this day 2, this day 3, this day 4. We're over here. We are out of days. And then we're just gonna, like I said, I start at 0. So if my day that I'm on is the total number of days, so if I'm on day 4 and it equals 4, that means I have no more days left. And if I'm not done with the tasks, that means this is not a valid way to do this. So if we don't have any days left, let's just return infinity. Now the recursive case is pretty straightforward. So because every day relies on the maximum task taken that day, we just loop from current index to the end and recurse at every point. And like how do we do this, and like what's the value we add and things like that? So let's actually write this down here and we can show that as well. So let's say we start at, let's get rid of this, put in the 8 again. So basically we're just going to have like a current value that's going to keep track of the biggest number so far in our loop. So we're going to have a current number, maybe it'll start at like 0, and then we'll have like our actual recursion. So we'll say like, okay, let's say we're over here, we're just starting, we're on day 0. Basically going to say like, okay, well, maybe we'll take this element and then this will be our task for the day, right? We'll just say, well, this is our task, this 7, and then we'll recurse. So our current element here, the biggest thing we've seen so far is a 7. And then what's our recursion going to be? Well, it's the total for the day, which is 7, plus dp of the next index, in which case it'll be 1, and the next day, which will be 1, right? If we start at day 0. Then we try to go to the next one. So we'll say like, okay, what about in this loop, what if we actually choose to take, instead of the first day, we choose to take the first 2 days? Well, the biggest number we've seen so far is 8 now, right? And so it'll be 8 plus dp of the next index, which will be 2, and day 1. So you just keep doing this, right? You just loop in every single dp, you just loop from whatever you're at to the end. You can have some checks to make sure like you don't run out of days, but because days is like 10, it's not really necessary, but you can do it. You can make sure like to leave a task for every day. So maybe like if you're on day 0, loop from, like here to here or something. If you want to, you can do that, but I personally didn't. And yeah, basically as you keep looping, you just keep track of the biggest element seen so far, and you add that to the dp of the next state, which would just be increment the day by 1 and increment the index to the next index from whatever you chose. So if we choose like this as our first day, then the next dp will be at index 4. All right, 1, 2, 3, 4. Yeah. And day will be 1 still, and the biggest element will be 8. So that's pretty much all you need to do. Is we have all these cases, and then that's literally all you need for the problem. It's not too bad. I think it's like maybe a tougher medium. But when I ran it, my runtime wasn't great, once again, because you can space optimize if you want to. I chose not to because, like I said, it's kind of repetitive, and it's not great for videos because it makes like 30, 35-minute videos to explain that. So I will, as always, add the space optimized video to that, but let's actually code it up and let's walk through all the steps. So we're going to have just a normal memoization solution as always. So we'll have a cache, and we'll have a dp function. And remember, we need an index, and we need the day. So if the index is the length of job difficulty, maybe we can get a variable there. So length of job difficulty. So if the index is that, then basically we have two cases. Do we have any days left? So if day equals d, that means we have no days left. We went through our days because remember we started 0. So for example, if days is 4 here, we're going to have like 0, 1, 2, 3. When we get to 4, we have no more days left. So, but you can start it at d and you can go down to 0. Like either one's fine, whatever you want. So if this is the case, we have no more days left. We just want to return 0 because that means this is a success. Otherwise, we want to return infinity, symbolizing like we have days left, so we never want this to be our best solution. Now, like I said, the other case is if our days is d, right? So if day is d, that means we have no more days left and we're not done. So then we just return negative infinity or infinity. Then we have the cache case as always. So if index day in cache, return cache index day. And now we have our actual like recursive case. So we're going to initialize our result to infinity because you always want to do this. If you're trying to minimize, you always want to initialize your result to infinity, go through all of your cases. And then if it stays infinity, that means you weren't able to find a valid case. So if this thing returns infinity, that means like there is no way to split this up. So that's what you want to do. Now we're going to have a current variable that's going to, remember, for each iteration of the loop, we're going to loop from our current index to the end. And we're going to try to take all the, like, we're going to, on every task, try to recurse and see what happens. So we're going to say for I in range, index, and length of job difficulty. So I think we have a variable for that. So J. Then we basically just minimize result here. So, and we also want to update current. So current is going to be maximum of current and job difficulty IDX, right? So keep track of the maximum, like the job that costs the most, and try to recurse at every single stage. So if we recurse, that's going to look like minimize of result and current, which is like the maximum task seen so far, and the recursion, which is just index plus 1. So if we take the job at index, we recurse to index plus 1, and we add 1 to the day. And that should do it. And now we just cache it. So cache index day equals result, return result. So now finally our DP will either have a number or it'll be infinity. So we just need to make sure that if it's infinity, we return -1. So we can say result equals DP of at index 0 with, so remember we start at day 0 here, and now our result will either be infinity or number. So we can just say return result if result doesn't equal infinity. Otherwise, let's return -1, right? Okay, let's try to actually run this. So it looks reasonable. And let's see here. Okay, it looks like we have an error. So let's just double check this. This is fine. All right, we're not using the current index we're on. And this should be the current index we're on as well. And I think that should be good. Let's take a look. Oh, this should be, yeah, this I plus 1 is fine. Okay, there we go. So like I said, it's a bit slower than like most uploaded stuff. So I think it's because there's like some more optimizations you can make. But this is basically the gist of the problem. Like if you do this bottom up or get rid of a dimension or, you know, make some slight optimizations, you can make it faster. But this is like the actual, you know, the main part of the problem. So I would recommend, at least if you've done like a ton of DP, it's not super important to try to optimize, like space optimize every single DP problem, because it just becomes kind of like a time sink. The main thing is just, can you get your states? Can you get your recursive case? Can you, can you get all your stuff filled out? And then as long as I would try to, you know, kind of like, for example, with like something like union find, try to space optimize maybe 1 in 10 or something, just to make sure, you know, if you do want to learn that you're still like good with it, but I wouldn't do it all the time. So let's go through the time and space for this one. So, yeah. And I think there is actually like, by the way, there is like another solution that's not DP that is actually faster. but I think for the purposes of like this problem, DP is pretty good, and for the purposes of an interview, the other solution is kind of hard to come up with. So I think this one's the better one to study and practice. That's another reason why I think a lot of them have a better runtime. Okay, and yeah, so for the actual time and space, so we have an index, we have a day, so index, and the nice thing is, yeah, for these constraints, index is only 300, so this is like 300 squared, which is like 60,000, and then day is only 10, so it's like uh, roughly 10 to the 6 or so, which will easily pass. But anyway, as for the time, so this is like n squared times the day. And for the space, this is n squared. No, sorry, n times the day. Now, once again, if you do want to optimize the way you would optimize, there's a few ways. No, I think there's only actually one way you can space optimize, because for the day, like this index actually goes anywhere from I to the end of the array. So you can't really space optimize that, but you can space optimize the day, right? Because every day the day increases by 1. So you can get rid of this day's dimension, and obviously, like an array solution will run a little bit faster. So you can cut it to just O of n space, and yeah, the runtime should be the same, but in practice it'll be a little bit faster as well. So if you do want to do that bottom up space optimize, this is the dimension you would want to get rid of. So that is something you should know, or at least if you want to, go deep into DP, that is something you should recognize, that if you did want to optimize this is the dimension you'd want to optimize. This one you can't, because you are looping from anywhere from the current index to the very end of the array. So you need all of them. So yeah, and I think that's going to be all for this one. So kind of interesting that they're giving you hard problems towards the end of the new year, but I don't think this one's too bad. I think this one's like a more slightly difficult medium. So regardless, if you did like the video, please like it, and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.